Login accepted.
Okay. Hello, my name is Artur, and I have a pleasure to share a pretty technical story with you today. Actually, that's why Marcin is here. But that's not the only topic we'd like to talk about. We're both coming from Jam, the software house from Poland, and at the core of our values is growth, like self-development, career planning, and so on. So this talk tells a story which is really highly correlated with the growth and career planning. If you're interested in these things, this might be also good for you.
Hey all, it's been almost 5 years since I joined Devoxx as front-end developer. Well, I knew some other languages. Artur, can I say it loudly? PHP. Yeah, but front-end was what I was doing mainly before. And actually, joining Devoxx was a big adventure for me. I barely knew English. I knew nothing about React, nothing about functional programming or any magic like that. And what really surprised me, actively working in many different projects, I still had time for self-development, self-improvement. And at some point, I met Artur, and it quickly turned out that we have a lot in common, especially making delicious tinctures.
Yeah. So imagine that you're head of development, who I am, and you're a huge fan of Scala, functional programming, or at least you think you are. And by accident, you're the only person in the company who has this experience, like Scala and backend together. And you're responsible for shaping technical vision, the technical stack in the company. You define what kind of projects you'd like to take. And once upon a time, you get a lead, which is niche of the niche, creme de la creme, blockchain and Scala combined together. And you feel that that's an opportunity you can't waste. But, well, you're the only person who you can assign to this particular project, apart from over-ambitious, over-self-confident front-end engineer.
Yeah, and the same story from the other perspective. Imagine that you want to learn Scala. You're a front-end developer, but you always observed the backend guys' work. You read a ton of papers, a ton of tutorials, you did few pet projects, and the slight chance of starting a backend project became a reality. One task, 2 weeks, Scala codebase. What could go wrong? Well, the client had a working blockchain solution. The problem was that it worked on paper only. The codebase was, well, a few thousand of lines in a single file. That was the domain part. Imagine all the services in the application in a single class, and that class was injected into every other class. Why not? That was dependency injection. So over first weeks, we worked with Artur till the early hours to basically understand the code base and to shine with our task. And only God knows how many anti-patterns we've seen over that time. When I try to remember our first task, well, we had to make a validation function. The choice was pretty obvious. Take the monad, validation monad. We lived in a functional programming world. Take the validation monad, do the stuff, return verbose errors. And it wasn't so obvious because we had to validate blocks. Blocks consist of some transactions. And to create a block, we need to know the parents, so also the blocks. It creates kind of graph structure, and we had to traverse through the historical blocks to verify if connecting parents together creates a correct block, because there could be a double spend or any kind of issue. So to fit with the existing code base, we ended up with a really cool, nice validation function returning a Boolean. Have I already mentioned that we spent weeks or later months fighting with Akka, with unit tests, with the code base? Well, there was a unit test creating a JSON file for a front-end visualization tool. So over that 2 weeks, in the existing code base, we found really exciting things. Like the whole solution was primarily written asynchronously. There were a few asynchronous parts, but they were deadlocking. Threads were most of the time blocked. There were unit tests, as I said, creating some visualization tools. Pure magic.
Yeah, I can recall these 2 first weeks pretty well also. I have teamed myself with a greenhorn who knows nothing about the JVM and backend programming at all, and the mat quality code base. Quick remark, the quality of the code was reasonable. I mean, it was a POC which had to prove it works. So it was written by data scientists, data analytics, and mathematicians. It could not be well designed. So it was a thing we had to deal with. In these 2 weeks, we wrote a single function, and still the client was happy about our progress, happy about understanding of the domain and the communication skills. And the other important thing which I have learned in these 2 weeks is that Marcin has exceptional mathematical and analytical skills. He's learning fast. He's picking up pretty quickly the Scala knowledge, and I can teach him. And together, we can deal with this particular project. Quick remark right now. Due to the NDA, we are not going to reveal the name of the project or some very specific details, even though we think it's like trivial to track it via the GitHub or any other tool, because the project is an open source. Anyway, we're going to obey the agreement we have, and that's all. Okay, let's move on to the topic. Back to the topic. Let's talk about high level about the project. So the product owner on the client side is a CTO who has great mathematical skills, knowledge about theoretical physics, and so on. And he is responsible for shaping the vision of the project. He gives us requirements, and we're responsible for the engineering part. What is the project about? Well, it's a blockchain 3.0, which means that we are trying to build yet another blockchain solution from the scratch. And the difference is, if you know Ethereum or Bitcoin, they have linear ledgers. And our ledger is a graph structure.
Yeah, and during this presentation, during this talk, you will hear the blockchain word many times. But in the context of our talk, it means exactly this, this structure, graph structure, instead of linear chain. And by using such a structure, the network can make parallel consensus rounds to create blocks. Let me quickly explain what is a block and how it connects with everything else. So there is transaction. That's a single point of data. And when transaction comes to the network, that's the very first step or the very first thing we need to propagate across the whole network. Then transactions are being put to the block by the consensus process, consensus algorithm. And the block also needs to be propagated through the network. Blocks have height determined by the other blocks, the parents. And every few heights, we are making a snapshot. The node is making a snapshot. And also the snapshot or the snapshot proposal needs to be somehow propagated as well. There is also a majority selection, which basically selects the snapshots or verifies if the snapshot is correct. And only then the data which are inside snapshot are being considered valid and correct. Well, over the last few years, we've been able to make a swap from ERC20 tokens into our own solution. And we launched a mainnet over a year ago. And believe me, that's a lot. We are currently integrating more and more exchanges. We are introducing new nodes, new foundation nodes to the network. And basically, we are preparing for the network opening.
Yeah, actually, what you're talking about is just the tip of the iceberg of the backlog we're working on, but it's not relevant to this particular talk. Let's get back to the topic. So at the stage of the project when we joined it, it was only a POC working on a single instance, so on a single JVM. What we had to do is introduce information exchange in the whole cluster of the independent nodes. So there was a requirement for information exchange, and by the information, I mean everything what's happening in the cluster, either it's the transactions or cluster health, anything. And to prove that it works in a distributed way, we picked a really naive and trivial approach, direct communication. So these nodes were just talking with each other with HTTP protocol. Well, it's a pretty obvious drawback for any kind of an app, either it's like distributed microservices or this kind of cluster. It makes this deployment tightly coupled. It does not scale due to this number of messages. Imagine that in such a cluster, each of the nodes is publishing n-1 messages where n is size of the cluster. And each of these nodes is also consuming n-1 messages because all of them are broadcasting information at the same time. So sending and receiving these HTTP messages is resource consuming. You easily reach limit of your resources. And of course, we can add nowadays a lot of CPU, memory, whatever it is, but still, you will deplete these resources in the inversely proportional to n² time. Of course, there are other drawbacks. Like you might think that this is the bare-bone copy of the code base deployed somewhere, so it's easier to implement error handlers or some business logic on top of the communication over the network. Well, maybe it's not such a big hassle, but still there is some randomness in the network, and this cluster is not deployed in a single data center. It's deployed wherever the node operators, so people who are launching these nodes, want. So it might be distributed over the whole Earth. There are so many corner cases, uncertainty, that there are a lot of failures in communication. And since of these failures, handling the errors on the level of the code base is really hard. Of course, we can have an error from a single call to the other peer, but we have to do something about that error. And the only thing we can do is start another broadcast. So we start avalanche of broadcasts, and in the end, we just kill whole cluster.
Yeah, and that's true. And basically, well, we have started with an application written in Scala that was pretending to be a node. One of our first tickets was about implementing a crosstalk consensus. And well, to create a crosstalk consensus, we need more than a single node. OK, consensus is a call algorithm, an agreement to validate the data and the correctness of transactions, of data, basically. So, for example, Bitcoin is a public blockchain where each node uses a proof-of-work algorithm to reach a consensus by competing to solve a puzzle. You must find a nonce value. And our implementation was and is actually kinda different. There is one owner and few facilitators in a single round. But as you can see on the screen, if you are the owner, you are also be able to participate in another rounds as facilitator. And that's why we call it a parallel consensus. Well, the consensus is divided into a few stages. First of all, the nodes need to propose transactions, propose data, then combine them together. Of course, this data must be validated. Basically, that was our first ticket we made in this project. And at the end, we end up with a block, or maybe no consensus agreement. And having a single node or 3 nodes, no one thought about big clusters. And I remember that smile when we connected 3 nodes all together. So you can guess what we did to share data over that network. A broadcast. Yeah, that was the obvious choice. 3 nodes only. What could go wrong? We made sure it works by adding a few timeouts there, a few timeouts there. Yeah, and at this stage of the project, we had plenty of issues with cluster stability, and I must admit that it took more than a year to make it properly working. And over that time, we had to somehow test how it works. So we're testing it using three nodes in the cluster, spin up in AWS. Every node is presenting detailed metrics that are later collected by Prometheus and visualized in Grafana. To spin up everything, to spin up infrastructure, we are using Terraform with some additional custom scripts for some maintenance, like joining the nodes together or starting from a single backup point. OK, we have the infrastructure, but we need to somehow develop it. So we are developing it locally, but I bet that not every one of you has a cluster at home. So we had to somehow send this changed application, locally changed, to nodes. And basically, it doesn't scale if you would like to send jar file to every single node separately. So what we did since the very beginning is to proxy it through S3 bucket. So we are developing locally. We are compiling the jar file locally and sending it to the S3 bucket. And then we are triggering all the nodes to fetch the updated version. And it scales pretty well, because last time we were able to spin up 300 of nodes in 10 or 15 minutes, so really quickly. Yeah, and if you only had seen me when I observed the Grafana for the very first time, I had no idea what I'm watching. Plenty of charts, CPU utilization, heap usage, garbage collector. I didn't work with JVM applications before. So thank you, Artur, for all your patience and basically you explained me all the details. And by the way, at the top, you see the tool written by Artur that shows you how the cluster or how the nodes see each other. Every single row is a local observation of a node, whether the other nodes are online or offline. So you see green or red boxes. And you see we had a chicken pop there. And then we realized that we have really serious issues. It looks like the communication between nodes doesn't work as expected. And after days of digging, we hit the nail on the head. Thread pools and resource acquisition. Book size topic, isn't it? And to be specific, we identified many synchronized places in the code base, and we started rewriting it piece by piece by incorporating IO monad to wrap effectful code. We told you that you don't need to know category theory specifics, so let me quickly explain what's the heck. You know, we are using functions. One can be pure, which means it has no side effects. It's referentially transparent. The other can be impure. So, for example, it has some randomness inside. It creates a random number. It relies on some external state or make an API call. And we cannot avoid it, right? So we have to deal with it somehow. And in functional programming, we strongly rely on pure functions and on immutability. So basically, we can delay the execution of side effects. And we can use the monad as a declaration what to do with the value, and the value will be provided at the very end. And basically, this is what a monad, IO monad exactly does. To use an IO monad, you must specify the thread pool where the execution must be made. And, well, I knew the only one, the global execution context. And of course, we use it for everything. Why not? In effect, API calls were deadlocking, timeouting. Why? No one knows. And there were many more things we did wrong, but we quickly repaired our issues. After all refactoring, we ended up with a pretty nice separation of what should be executed and where. We used the pattern presented by Daniel Spiewak. In a nutshell, we used 3 thread pools to handle all the operations. The first is a bounded thread pool for all the CPU-heavy calculations. The second, non-blocking I/O for handling API requests, or basically it's for handling asynchronous events from the kernel. And the third one for blocking I/O, basically for all the other stuff. Well, the bounded thread pool is fixed to your CPU cores. So imagine that you have 4 cores, so you have 4 threads. And imagine that you are making some delays, you are blocking all the threads, you are out. So you must avoid blocking the bounded thread pool at all cost. The second thread pool, it's called sometimes event dispatcher or scheduler. Basically, it's for asynchronous events, and I had really no idea how to use it and how should we use it. So I read that it's for maintaining all the threads, green threads, fibers. Basically, when you delay something and you do that on the other thread pool, at the end, the scheduler receives the event that, OK, that job is done. You need to proxy it there. And basically, the blocking I/O is a cached thread pool, so there is no size limit. Well, there is a limit memory on your instance. But basically, that's the thread pool you should use for all the blocking operations. And fun fact, I read a few days ago in the CATS documentation that in the Java, there is a URL class. And that class has a equals method. So basically, you use it to compare two URLs together. And that class also, in the constructor, makes a DNS resolution. So every time you want to compare two URLs, you are making DNS calls. And what's more interesting, it's not a Java code, because to make a DNS resolution, you must call the native function from your operating system. And everything is blocking. So if you have plenty of URLs to compare, or you have a URL in the key of your map, as a key of your map, you are blocking all the threads. So be careful. One does not simply. No one told us that jumping between threads isn't so straightforward. When you jump, you need to go back. And you must be sure that you are going back to the correct pool, of course. And, well, I could tell you more, but we are moving away from the main topic. So please catch us later. We'll be next to the EvoJam stand.
Yeah, after these months, Marcin got pretty good backend experience from Scala, JVM, math, of course, only for this particular type of projects, but still. The team that has formed around him was capable of dealing with the project on their own. Like, my role was more like consulting on the level of architecture, being a rubber duck, and helping them on a daily basis, but really from distant perspective. Additionally, the functional constructs that they have introduced were way beyond my practical and professional experience, so I no longer could understand what they're actually writing.
Yeah, the funny thing is that I have totally other vision, and I think I know almost nothing, maybe some basic concepts. By the way, if anyone is interested in category theory, I can highly recommend a really great book written by Bartosz Milewski called Category Theory for Programmers. It helped me taste a little bit of why functional programming looks like it looks, to learn basic concepts of functional programming, and basically it's a book I'm constantly going back to.
Yeah, that book is great. I have it at home, even the printout, but please don't ask me if I ever read it. Let's get back to the topic, because actually we've spent a lot of time on the details which Marcin really likes as a software backend engineer, and we promised you to talk about communication, not optimization of the code base. So what could we change in the system to scale it up, because we reached in this kind of scaling, optimizing, and refactoring some kind of a limit? Well, pretty obvious thing which we might think about is a message broker. Any kind of a message broker would work here, because instead of publishing n-1 messages, each node would publish a single message, and other nodes would consume it at convenient time. Well, it would be scalable, resilient, especially if you use distributed Kafka cluster, which spans multiple physical data centers, and so on. Well, technically, it's correct, but remember, we are building a blockchain cluster where nodes are operated by separate individuals, and they are responsible for deployment, maintenance, and so on. So this particular message broker would be a single piece in the architecture which has to be controlled by someone. And I cannot imagine that this kind of a thing can be maintained by community, especially that some of these guys are not really technical. So in the end, we would introduce a single piece, which is controlled by someone who, in the essence, has a control over the whole system, because they can affect stability and transparency of the communication. So even though this kind of a solution would fit us technically and would solve our problem in terms of scalability and resilience, it's not for us. So the question here is, if we cannot let anyone control the whole blockchain, what else we can use? And if you are familiar with architecture of Bitcoin, Ethereum, there is a solution for it, and that's the core of our talk today. It's a gossip protocol. So the gossip protocol, the name of the protocol itself, nicely reflects how it works. If we pick a single node which wants to spread a new message in the whole cluster, it just broadcasts it to some number of peers, and well, they get a new message and broadcast it further and further. And statistically, at some point, you will get the eventual consistency in terms of that particular message in the whole cluster. The interesting part here is how many peers you should notify with that message. It's described by a Fanout, which, for example, can be set to 2. And for this particular cluster, it's set to 2. How to calculate, how to estimate when the whole cluster will be eventually consistent? Well, it cannot not be set exactly because there is some randomness in selection of your peers. So we rely on a statistical equation, which is pretty simple. It's a logarithm base of Fanout from size of the cluster. And if we calculate it, it looks like it's pretty scalable, because for 100 of nodes and a Fanout set to 2, the number of rounds of publishing this message is the same as for a cluster which has 1,000 of nodes and a Fanout set to 6, and for a cluster which is 5,000 of nodes and a Fanout of 10. And it scales nicely, because sending few messages like 2 or 10 or whatever isn't that much resource consuming, so we can easily scale, and number of rounds here is around 4. So the message spreads in the whole cluster really quickly. Well, that's a simple gossip approach, and it works if these nodes are treated as equal, if these are like local nodes. What happens if the cluster is more complex? Well, then we might want to introduce some additional tweaks and things to the gossip protocol. For example, calculating the peer choice on top of a distance. Either it's a physical distance or a network latency, anything. We can calculate which nodes should be notified by a particular one, which peers he should choose to notify these nodes. There is similarity, and we promised to tell you about this kind of similarity with epidemic models. The distance is the same what we have in the pandemic modeling and viruses. We have additional similarities, the reproduction rate. So in pandemic model, we have R, I guess you know. Here we have a Fanout, and we can increase Fanout to spread messages faster to reach more nodes. Well, there's a drawback. We have a huge network congestion. The more messages, the more duplicates, the more reproduction on this level means it might kill the cluster again. So what we can do, we can change stop conditions for spreading messages. And the two popular approaches are, first, we can just have kind of like a DNA replication model capabilities. So the message has kind of an age. When it's republished a couple of times, the node stops republishing it because it aged. And the other approach, which is more complex, is the peers can track how many of the nodes were already infected, so who already knew about this particular message. If they reach a limit, they just stop spreading because they assume all of them statistically should be aware about that message. And it works well if you have a cluster which is complex, which, for example, reflects some physical concept like Earth. The gossip protocol scales nicely, can be tuned further. Does it have any drawbacks? Of course, yes. The first one, the first obvious drawback, can be explained on top of the popular game.
Yeah, have you ever played Chinese whispers or broken telephone? The first player has a message and whispers it to the second one to the third one, and so on and so on. And the last player needs to confront what he heard with the original message. And I bet you know the results. You know, I'm creating a transaction for $100, and the last node thinks it's 1,000. So basically, it's often invoked as a cumulative error, especially in kind of spreads like gossip. And in the classical gossip algorithm, every participant can modify the message and forward the new one, a changed one.
Yeah, you nailed it. So basically, that's one thing. One malicious behavior can poison the whole cluster, and the other unaware victims will just legitimize the message that has been modified on the fly. The other thing is that the gossip communication is highly redundant. And it's cool for immutable information sharing. So if you want to broadcast some information in an effectless way, it's great. But what happens if this redundancy, on top of that redundancy, we want to build some business logic? Well, we would have to track when we trigger that business logic. And in our case, nodes have a thing called a reputation. So we treat some malicious behaviors differently and act on top of them. Well, this kind of application might lead to false positive reactions and would destabilize the whole cluster. It's really hard to build a business logic on top of the gossip protocol, especially this plain one, and that would affect stability of the whole cluster. We had to pull some additional weapons and modify the algorithm in some way. And one thing here, that's the point in the project where actually I lost track on what's happening. I realized that Marcin is a true technical rock star, and he only knows what's happening in the project. I cannot tell you that much more about details. So now Marcin will tell you how gossip protocol works in this particular blockchain.
Thanks, Artur. And instead of asking, you can just go and cry to a shoulder.
You're always welcome, dude.
Tough. OK, so let's sum up what we know about classical gossip and why it's not enough for our use case. First of all, and in my opinion, it's the most important, that we need to go away with the unhealthy nodes. And we only need to talk with the best nodes if the cluster needs to run as fast as possible. And our blockchain solution strongly relies on reputation, on trust and reputation. Well, the trust is a local observation on every node. And when the trust is being converged and aligned, it becomes a global thing, a reputation. And both takes value from -1 to 1. Simply, nodes with better reputation are considered to be more reliable and stable. And I said that trust is a local observation. So assuming I am a node, from my point of view, I can sort the nodes by trust. So you can see there that on the left, on the beginning of the path, I have the nodes that I have a better connection with. And on the last nodes are the nodes that are dropping packets or are somehow unstable. And that's basically the first driver we need to consider. Talk to the nodes that are more reliable, more stable than the others. The second drawback of the classical gossip algorithm, also significant, is that there is no proof the gossiped message is original. OK, so how to deal with that? Well, in blockchain solutions, we strongly rely on cryptographic keys a lot. And basically, it's a base of every blockchain or cryptocurrency. So here in our project, we generate a wallet address from the public key, as usual. But also, we have a kind of node identifier, which is a one-to-one correspondence to the public key. In functional programming, we call it isomorphic. So in other words, we can go back and forth from public key to node identifier. And these identifiers are being exchanged during the joining process. So basically, nodes exchange this information between. That being said, every node knows all the identifiers, so also the public keys. And we can use that fact for our security issue. How? Well, every node can sign the message before passing it to the next peer, signed by using a private key. And the receiver can, of course, verify whether the message is original or no. But I think it's not enough. We don't need to check whether the person or the node who sent us the message is correct and the message is correct, originated from him. But we also need to verify the whole path because it's possible that it's not the previous node isn't an owner of the message, but someone else. And basically, we call it a cumulative signature, where nodes are adding the signature to the existing ones instead of creating a new one and just passing that one. So we aggregate all the signatures during the path. It led us to the second driver, security. So we already slightly changed the rules for gossip protocol. And we told you that gossip has some randomness. It selects the nodes to gossip in near real time. But there is a problem because you cannot verify the path if there is no path at all. So we need to create paths somehow. Well, it's a job of the service called partitioner who takes the Fanout, and the Fanout here specifies how many paths we should create. Also, the locally sensitive trust is being used for determining how nodes should look like or how the path should look like, so the better nodes at the beginning. And it means that every node can select a different path for forwarding the messages. And over some time, the nodes should select the best paths to proxy messages through, and hence there is no more randomness in the gossip algorithm. Fine, we have trust, reputation, we have best paths, we have signatures, and still it's possible that the message would fail at some point. What to do then? Among many different solutions, we've chosen two steps failover. The very first step used in our gossip implementation is a bisect algorithm. The method consists of repeatedly dividing the path into two parts by selecting a middle point, or somehow middle, in the middle, and checking if the node received the message. If yes, skip the left part. And check again, select the middle point. The node didn't receive the message, skip the right path. And that way, we are able to quickly select and find the node who failed, or basically the message failed somewhere in between. As the second step of failover, we use a custom solution per each type of data. And we are currently using gossip for snapshots and for blocks. For blocks, we use an algorithm that compares hashes. So basically, it compares the consistency of data among the nodes. Every node creates a hash, a single hash from all the accepted blocks at a particular height, and also the global hash of all these previously created hashes. So simply by comparing only a single string between the nodes, we are able to say, OK, there is something different accepted. And if that happens, the node needs to realign. So it needs to basically fetch the missing parts or somehow redownload the missing data. And the second failover step for snapshots. Well, do you remember what a blown filter is? It's a data structure designed to tell us whether the element is present in the set. The price is that it's a probabilistic data structure. So it says that either the element is definitely not in the set or may be in the set. Well, we use Kaku filter for snapshots because it allows also for removal. So it allows us to remove data from this set. And the guy who proposed that idea sitting there, thank you, Tomek, that was really brilliant, and it works pretty well in our case. Basically, that structure is being shared with the nodes. Among different data, we are also sharing. So it's not a single or individual gossip. And when nodes are misaligned, they probably know which nodes should be asked for data. Great. And it looks like we did a lot of work to make this project happen. And that's true. It took us more than 2 years to make it properly stable and to launch a mainnet, and an additional year to handle the scalability issues at the satisfactory level. And as the next steps, we decided to move to UDP instead of TCP because we don't need this retransmission rate. And basically, UDP is faster in that case. and many failover algorithms handle it better, at least for our case. And the second thing is that currently we are using Gossip for blocks, for snapshots, but there are many more things that nodes are exchanging between each other. So we plan to use the Gossip as a base algorithm for our use case. And basically, it's not the end of growth and R&D in the project, because we already started implementing the improved core that will allow for processing and validating third-party data from other blockchains or different data sources like IoT devices. And the whole concept has been transferred from a math paper into Scala code base, thanks to Cats library, thanks to Drosty library. Drosty is really cool stuff for recursion schemes. Check this topic out. And in that improved core protocol, the Gossip algorithm, since we are talking about that all the time, is implemented as a core algorithm for data synchronization, for information exchange. And basically, we aim for massive clusters. So basically, that's the only efficient way to keep it scalable, to make it happen.
OK, guys. Thank you for listening. That's all what we wanted to tell you. We left some time for Q&A. I hope that each of you could find something what was inspiring, encouraging in terms of growth or using new technologies or looking at a blockchain. We would love to talk with you face-to-face. You can talk to us via our Meet booth, or physically we're on the first floor. You can reach us out there. We would love to get your feedback. The topic is pretty complex. Actually, Marcin is sharing a lot of details, so we would love to hear back from you. How did you like it, or what you would like to hear more about? There are our Twitter usernames. If you want to follow us, we will tweet occasionally about the project status, new milestones reached, and so on. So please just follow us. Thank you.
Thank you.
Koniec. To postoimy tu jeszcze chwilę, nie?
Oczywiście.
Tak? No.
Nad samym codebase'em około 4-5 osób. Natomiast cały projekt wymaga zaangażowania też większej ilości osób, wiadomo, marketing i takie rzeczy, więc to już jest większy zespół. Ale stricte jeśli chodzi o kod, to 3-4 osoby mniej więcej.
Właścicielem jest firma ze Stanów, która nam go zleca. My dajemy ten engineering team dla tej części, nie? Tego core'owego blockchaina. Oni mają po swojej stronie zespoły, które się zajmują resztą, tą toczką całą, natomiast my piszemy całe to rozwiązanie i technicznie za to akurat odpowiadamy. Tak, no, jest to open source, więc mimo wszystko jak ktoś chce, no to może sobie tam popatrzeć. No, to jest ciekawy model, nie? No bo jest to w pełni open source'owe.
Czy prowadziliście sobie takie symulacje? Ile w zasadzie, czy na przykład jest taka szansa, że będziecie kiedyś potrzebowali tyle nodów, że wam zabraknie na przykład pamięci do przechowywania tych danych? Czy to są na tyle małe te dane, na tyle mało, że to nie wybuchnie?
To znaczy tak, metryki mamy cały czas podpięte i cały czas obserwujemy, jak to rośnie, w miarę jak dołączamy kolejne nody. I wiadomo, że nic się w nieskończone się będzie skalować, ale jest kilka różnych podejść, jak sobie z tym poradzić. Między innymi na przykład tak zwany partitioning, czyli dzielenie całej sieci na jakby mniejsze grupki, które sobie będą współpracować razem i traktować to jako taki jeden byt. Nie?
To jest takie unikalne dla tego projektu, to jest to, że My tu mówiliśmy o tym, że te dane są trzymane w formie grafu, ale tak naprawdę gdzieś na koniec końców to cała sieć ma być takim grafem z podgrafami, nie? Hypergrafem. W związku z czym no to, o czym powiedział Marcin, w tej chwili monitorujemy te parametry i być może tam jakieś techniki trzeba będzie kiedyś zastosować, żeby to się skalowało, ale tak naprawdę to rozwiązanie jest inne, nie? Rozwiązanie jest zrobienie hypergrafa z tego. Tak. No.
Trust, reputation? Wiesz co, cały czas jakby też nody zbierają informacje o komunikacji. Przykładowo nie w tym sensie. W tym sensie, że na przykład mamy konsensus, wybraliśmy na przykład 3 nody do zrobienia konsensusu ze sobą i nagle okazuje się, że jeden z tych nodów w ogóle nie zrobił proposali, albo zrobił proposal i już nie zrobił nic więcej, nie? Na przykład jest, nie wiem, kontrolowany przez takiego operatora, który próbuje coś złego zrobić, nie? W sensie taki malicious node.
Ale też może być tak, że po prostu operator przydzielił bardzo mało zasobów dla noda, nie?
Faktycznie.
To też się zdarzało dość często, że one są niestabilne, bo mają bardzo mało zasobów i no niby działa, ale nie przestaje odpowiadać nagle.
Albo jeżeli wiesz, tych danych jest za dużo i tych procesów jest za dużo, no to działa dużo wolniej. Gdzieś wpada na przykład w któryś timeout. Więc w tym momencie jakby zapisujemy sobie taką obserwację. OK, ten node nie zrobił tego, nie? Albo ten node w ogóle, nie wiem, chciałem od niego pobrać dane, a on nic nie ma. Więc
tak.
pewne obserwacje sobie... Nie, w ogóle każdy node jest... To jest zdecentralizowane, nie? Więc każdy node jest utrzymywany przez całkowicie inną jednostkę. Tak, jak najbardziej.
W tej chwili sieć jest jeszcze zamknięta dla
Przygotowujemy się do otwarcia
tak.
w najbliższych miesiącach.
No. I tak naprawdę te opóźnienia na sieci też będą miały wpływ na te obserwacje, bo możesz nie zdążyć, coś się nie wydarzy, nie? Ale to nie jest tak 1 do 1 to skorelowane, że patrzymy na latency i mówimy, no, że on jest wolniejszy, to ma niższą reputację.
Tak, no ale właśnie wtedy te obserwacje jakby wpływają wtedy na trust, nie? Mają jakąś wagę na przykład i tak dalej. No i nie wiem, po 3-4 razach jak się nie uda z tą skomunikować, no to uznaję, że okej, no to już na przykład więcej już cię nie będę pytał, nie? Albo spróbuję dopiero za godzinę, a nie za chwilę.
Spoko. Dzięki.
Dzięki.